Good afternoon, everyone. Myself, Laishram Saya, and I'm an assistant professor in Sri Venkateshwara College, University of Delhi. My today's module is related to conductance only, and it is in continuation with the last module. And by now, according to my last module, I hope all of you must be well aware of the fundamental concepts related to conductance. So today, I'm going to pick up a very interesting topic related to conductance, that is the variation of specific conductance as well as the molar conductance with concentration. And it is found that the specific conductance increases while molar conductance decreases with concentration. So why such a difference and variation in specific conductance and molar conductance with concentration? Why is it observed? We have the basic equation relating the conductivity G, the conductance G with the specific conductance kappa, according to which G is equal to kappa A upon L. And from this equation itself, it is evident that the conductivity kappa, that is the specific conductance kappa, is directly proportional to the conductance. And it is also quite obvious that this G, that is the total conductivity, takes into account the conductance contributed by all the ions in electrolytic solution. And as if we increase the concentration of any electrolytic solution, and it is quite obvious that the number of ions will also increase, whether we talk about um, weak electrolyte or whether we talk about strong electrolyte. The total number of ions is going to increase in an electrolytic solution as the conductance increases. So that's why total conductance increases, and as the specific conductance is directly proportional to the total conductivity, the specific conductance is obviously going to increase. So that explains the fact. But what happens in case of molar conductivity is we have this basic equation relating molar conductance with the concentration C, where we can see the appearance of the specific conductance kappa also. Lambda molar is equal to kappa upon C. And as already described above also, as we increase the concentration, kappa is going to increase, and the denominator side, that is the concentration, is going to increase. So in this case, the factor, we have to decide the factor which is increasing faster, whether it is the concentration or whether it is the specific conductivity term which is increasing faster. And it is observed that the increase in kappa cannot cope up with the increase in the concentration. So that's why we can see an overall decrease in the molar conductivity if we increase the concentration. And this variation of again, a very interesting thing here is the variation of this molar conductivity with concentration, that is the decrease in molar conductivity with concentration, can be explained in different ways in terms of whether it is a weak electrolyte or whether it is a strong electrolyte. In case of a weak electrolyte, it is explained on the basis of Arrhenius theory of electrolytic dissociation and Ostwald's dilution law. The combination of these two will give us a very good explanation of the variation of molar conductivity with concentration. But in case of strong electrolyte, what is more interesting here is, in case of strong electrolytes, we have to introduce a new theory which is known as a Debye-Huckel-Onsager theory in order to explain this whole variation. So coming to Debye-Huckel-Onsager theory, this theory has been proposed by Peter Debye and Eric Huckel. And according to Debye-Huckel-Onsager theory, this is the basic fundamental concept behind Debye-Huckel-Onsager theory. That is the working principle, you can say. Each ion in solution, whether it be a cation or whether it be an anion, it is surrounded by an ionic atmosphere. So what do you mean by an ionic atmosphere? Ionic atmosphere is nothing but it's composed of ions of opposite charges to that of the central ion, hence giving a net average charge opposite to the central ion.